you all to the first session for the novel technologies for food processing and shelf life extension. So in these classes, both that will be happening on Saturdays and Sundays, we will be taking up previous year's assignment questions and other questions that were a part of the earlier exams, and we'll be trying to solve those in these sessions. And if you guys have any doubts pertaining to the lectures that have been uploaded in the NPTEL, you can either post it in the discussion forum or you can bring it up in these sessions. So if we know the answer, we'll explain it to you then and there, or else we'll get back to you as soon as possible. So this week we'll start with the first week 1 syllabus, where we'll be solving some assignment questions and other sample problems. So whatever assignments that is now given in the NPTEL portal will not be solved until the deadline is over. So once the deadline is over, then we can discuss those questions. But before that, we'll be discussing some sample problems that might help you in solving the current questions. And one small request, please try to join the class at 4 itself so that there's not much disturbance while the class is happening. So we'll move on to the first question. Identify the steps A, B and C in the following schematic of the food product development and engineering. So if you guys know the answer, you can post it in the group chat, or you can unmute yourself and answer. So any idea as to what the answer could be? What is A, what is B and what is C in a food product development scheme? So what is required to identify the need or opportunity that is present in the market right now? So we require engineering resources, kind of survey systems or other financial resources to first figure out what is the need in the market right now, what kind of food products, what is the product that is already available, what are the limitations in those. So first we need to find out the need and opportunity, and that is ensured via engineering resources as well as financial resources. So once a need is identified, what we need to do is we need to understand how to meet those needs in the market. So in order to meet those needs in the market, we need to develop a concept or an idea as to how to produce the food and how to store it. So we need, after identifying the need, we need to develop a concept to match those needs and to meet those needs in the market. So once a concept is developed, what we generally do as in an R&D process or so is we start with a small scale test setup or a reaction setup, where we'll develop the food products, or we'll store the food products in a small scale. And once that is successful, we'll start slowly scaling up the volume. That is, if we start with say somewhere around 2 kgs of a food product, we'll start scaling it up to 200 kgs or so. So at each stage when you scale up, there are multiple challenges that we face, and it is not necessary that at each stage you will actually have success. There are times where when you scale up, there's a lot of chance of failure as well. So when there is a failure in any of the subsequent stages, we go back to revising the concept. So if there is any problem in in meeting the needs, we'll go back to the concept revision. We'll change certain conditions so that now the process will be successful at a higher scale as well. So at multiple scales, make sure that the food product is developed according to the safety and the quality standards. And once that is successful, we will go to national production. So the need or opportunity for a particular food product in the market is first investigated using resources, which is A, and then we develop a concept to meet the needs, which is B, which is developing the concept, and C involves national production, that too after successful trials at various scales of food production. So the answer is option A. If you guys have any doubts, you can stop me anywhere. If I'm going fast, you can let me know as well. We'll repeat the question again. Is this clear? Can I proceed to the next question? Are you guys able to hear me? Can I proceed to the next question?
Yes, ma'am.
Okay. So question 2. Which among the following microorganisms is only inhibited by lowering P by P naught less than 0.65 to 0.6? So there are 4 organisms options given here. But before we discuss that, does anybody know what is P by P naught? Have you guys gone through the lecture videos of this particular week, or should I be explaining those concepts before we go in? So what is the term P by P naught? What is P here and what is P naught here? Okay, so if people are unable to come up with the answer, I'll explain each and every concept. So if you guys don't understand a certain concept, you can ask me to repeat again as well. So P by P naught, P is a partial pressure of water above the sample. So if you have a certain food product, you keep it inside a chamber and let it equilibrate with the chamber. So P is the partial pressure of water above the sample, and P naught is the vapor pressure of pure water. So that's the reason why we estimate P by P naught for each and every food product that we are producing. So P by P naught, also known as the relative vapor pressure, can also be termed as water activity. So this water activity gives an idea about the food stability and the how much organisms could possibly grow in that food. So basically, microorganisms require water for its growth. And if you have a certain amount of water in the food, also known as the water activity, then that might promote this growth of the microorganisms in the food, which is not something that we want. We want the food to be as safe as possible to consume. So when by estimating P by P naught, we know what is the water activity in the food, and accordingly we can have some idea about the food stability as well as the microorganisms growth in that food. So each microorganism has a certain water activity level in which it can thrive, below which it is very difficult for the organisms to survive. That is because when the water amount gets very less inside the food, the bacterial cells or any microbial organisms undergo some sort of an osmotic stress because of unavailability of water. So because of this unavailability of water, it undergoes stress and then it becomes dormant. So what we generally do to ensure proper storage of food is that we make sure that the water activity in the food is drastically reduced. When we reduce the water activity, the amount of water in the food reduces and the microbes become dormant. We do not kill the microbes, we only make the microbes dormant, which is why it is preferred to have a low water activity in the foods. So P by P naught is actually the water activity in the food that will give us an idea about the food stability and the growth of microorganisms in the substance. So the growth of Saccharomyces rauxi, one of the organisms here, is inhibited only when the water activity is lowered below 0.6. Whereas the other organisms mentioned here, Clostridium, Staphylococcus and Vibrio, are inhibited when the water activity is lowered below 0.95, 0.8 and 0.91 respectively. So lower the water activity, lesser the chances of the microbes to survive. So hope this is clear as to how water activity is related to microbial growth. Only when there is not presence of water, only when there is a lack of water or a depletion of water, will you be able to inhibit the growth of microorganisms. And Saccharomyces requires very low waters. It is able to survive even in low water activity conditions. That's somewhere around 0.6. Sorry, any doubts? Okay, so Saccharomyces is able to survive even at low water activity foods, that is around zero point 0.6 as well. So only when you reduce the water activity even below zero point 0.6, you will be able to inhibit the growth of the microorganism. So the answer to this question is option B. So in any of these sessions, if you, at least in this session at least, if you find that this part of the question was not there in the video lectures or so, let me tell you that this was there in the
Ma'am.
assignment question, and these are all from the book of Fenema's Food Chemistry. So if you want,
Yes,
you can
ma'am.
refer back to this book for further details. Should I explain it again? So water
Yes,
activity.
ma'am.
Okay, so water activity is basically the amount of water that is present inside the food. So this can be in the form of bound water or any basically water present inside the food is a measure of water activity. More the water present, more is the water activity. Is this clear? So if you have a very milk, like milk will have a higher water activity, whereas cereals or crackers or biscuits will have a lower water activity because those are all dry substances. Whereas liquid or things that are very wet have a higher water activity. So higher water present is equivalent to higher water activity. So microorganisms can survive only when a certain water activity is present inside the food, because all organisms require water to survive. Only when you completely remove the water, you will be able to inhibit its growth. Is this point clear as to how water activity is related to growth of microorganisms? Okay, so microorganisms require water for its growth, and you have to remove that water in order to make it dormant. So, among these four organisms, these three organisms, that is Clostridium, Staphylococcus, and Vibrio, are inhibited at higher water activity itself. That is, if you even if you slightly remove the water, it will be inhibited. But in case of Saccharomyces, it can survive even in dry foods. So you have to make it extremely low. You have to make the water activity extremely low, that is below zero point 0.6, in order to inhibit Saccharomyces. Is this clear? So the entire concept of water activity is very well thoroughly explained in the lecture 4 of the course. You can go there for further details as well. So the answer to this question is option B, which is requiring very less water to survive. So you need to remove those water as well to inhibit its growth. So P by P naught is a measure of water activity. This is something that might come up in numericals as well. So you need to remember this. Moving to question 3. Which among the following statement is not correct with respect to the image given below? This image represents the conformity of important deteriorative reactions in food to the Arrhenius relationship. Above a certain value of temperature T, there may be deviations from linearity due to a change in path of the reaction. C, as the temperature is lowered below the freezing point of the system, the ice phase enlarges and the fluid phase, which contains all the solute, diminishes. D, for an enzymatic reaction, there is a temperature in the vicinity of the freezing point of water where dissociation of the enzyme complex occurs, leading to inclination in the reaction rate. So this was also discussed in the lecture videos. So if you guys remember seeing this graph, can you explain what is happening here? Can anybody explain what is happening here? What is this graph that you're looking at. So when you have food that is being stored, or when you're producing certain foods, there are always some reactions happening, like say hydrolysis of lipids, oxidation. All these processes are happening. All these reactions are happening that can make the food less stable or less available to consume. So that is, these are known as deteriorative reactions, where you have some unfavorable changes happening inside food that will happen throughout your production processes or happen during the storage processes, because you're subjecting the food to various kinds of conditions. So in all those cases, there will be some kind of a deteriorative reaction that is continuously happening, resulting in reduction in the quality of the food throughout the process. And when we talk about reaction rates, if we understand 11th standard chemistry, we know that the reaction rates are often following something known as the Arrhenius relationship. Are you guys familiar with the concept of Arrhenius relationship? Okay, so the reaction rates, any reaction rate as say, are dependent upon temperature, and it is often said that this reaction rate follows something known as the Arrhenius relationship, where K, which is your reaction rate, is equal to A e power EA by RT. K is your reaction rate, EA is the activation energy, R is the universal gas constant, and T is the temperature in Kelvin. So this is the Arrhenius reaction rate. So any chemical reaction rate assay is generally known to follow this Arrhenius equation. So how do you find out the activation energy? And so is that if you take a logarithm on the both the LHS and the RHS, that is log K is equal to log A minus EA by RT. Sorry, there's a negative sign here which I forgot. Minus EA by RT. So if you plot a graph between log K and 1 by T, minus EA by R will be your slope and log A will be your constant. So this is actually equal to y equal to mx plus c, which forms a linear, which is a linear equation. Are you guys aware of this? Are you able to understand this? That when you plot log K and 1 by T, you will get a linear relationship. It's my kind request that please join the class on time, so that we don't have to go back and forth with this. So K, if you plot log K, which is log of the observed reaction rate, this is 1 by temperature. Here it is written K my inverse, which means this is actually 1 by temperature. So if you plot log K, which is 1 by T, any reaction that follows the Arrhenius relationship should give a straight line as seen here. But sometimes, at least in the case of food products, we see that at certain regions in the temperature range, we do not get a straight line. That is, the Arrhenius relationship is followed only in a certain temperature range, but above and below that, the linear dependence kind of goes away. Are you able to understand this? At very low temperatures and at very high temperatures, you see that there is no linear dependence, but only in the middle range, somewhere in a minute temperature range, you can see that there is a linear relationship. So this is because of various reasons. This non-linearity could be because of change in reaction path. That is, when there are multiple reactions happening, suddenly there will be some other reaction that is dominating, some other deteriorative reaction that is dominating at a certain temperature. So now your reaction path changes. That could be one of the reason. Second thing is that when you're dealing with enzymatic reactions, say if some kind of hydrolysis is what is causing that reaction, those hydrolases are active only at a certain temperature, because enzymes are all proteins. They require a very small range of temperature for optimum activity. Above and below this temperature, the enzyme will no longer be active, and hence the reaction rate will also be different. So loss in enzymatic activity is also one of the reason why you don't see a linear relationship. And third reason is change in physical state of the system. So if you bring down the temperature drastically, you might either freeze the system, or if you increase the temperature drastically, you might end up boiling the system or vaporizing the system. So the physical state of the system highly depends upon the temperature, and if you change the physical state of the system, again your reaction rate will also differ. And depletion of reactants. Over the time, if your reaction keeps on proceeding, at some point of time, your substrates will kind of get depleted. At that stage, when your reaction depends upon your substrate concentration, it will no longer follow a straight line. It will have differences in the linearity. Is this understood? Why we don't see a linear relationship at higher or lower temperatures? So this to to explain all the points here, this image tells us how the deteriorative reactions change with temperature. So above only in a certain temperature range you see a linear dependence. Above a certain value of temperature, like say for higher the temperature, lower is 1 by T. So you need to mention that this corresponds to higher temperature. This corresponds to lower temperature. We are looking at 1 by T and not T here. So keep that in mind. So at higher temperatures, we can see a deviation from linearity because of change in path of the reaction, which can happen when there's a higher temperature. Some other reactions might start happening, and hence there will be a change in path of the reaction. Hence, statement B is also true. Statement C, as the temperature is lowered below the freezing point of the system, the ice phase enlarges and the fluid phase, which contains all the solute, diminishes. So when you start freezing the system, you will see that the water will start crystallizing into ice. But only the water will crystallize. Any other solute that was present will remain in the minimal amount of fluid that is present. Like say if 50% of the food has now become ice, whatever solute was there will now be present in the rest of the 50% only. So you will see that the entire solution becomes extremely concentrated, and sometimes the high concentration of the solute will actually inhibit the reaction, like a kind of substrate inhibition are all present. So if you have too much of concentrated samples or concentrated solutes also, that might also diminish your reaction rate. And other thing is, reactions require certain amount of water to occur. If water itself starts crystalline out, then your reaction rate will also drop. So C is also correct. If your temperature is lowered, your ice phase will start enlarging, fluid phase will reduce, and thus that will affect the reaction rate as well. But for the D option, for an enzymatic reaction, there is a temperature in the vicinity of the freezing point of water where dissociation of an enzyme complex can occur. So, if an enzyme and substrate complex that is formed breaks open, then there is no longer a reaction that can happen. At this low of a temperature, your enzyme is very, very sensitive to any small changes. So even if there is a small dissociation of the enzyme complex, the reaction rate will drop drastically. So this will not lead to an inclination in the reaction rate. It will lead to a declination in the reaction rate. If you guys don't have any doubts, please mute your mic. Keep your mic open only to ask doubts or answers, please. So is this clear? Why is D wrong? So at very low temperatures, even subtle changes such as enzyme complex dissociation will result in rapid declination of the rates. If your substrate is not binding to the enzyme, the reaction will not happen. So if it dissociates, you will have a declination in the rates. So option D is the one that is false. So all these lecture videos and the lectures will be posted in YouTube as well as all the Google Drive that we'll be sharing pretty soon. So you guys can refer back to these slides anytime you want. Okay, moving to question 4. Identify 1, 2 and 3 in the following schematic of summary of the chemical interactions among major food constituents. So 1 is here, 2 is here and 3 is here. So what do you think one is? So what are the major constituents in a food? Three major constituents or biomolecules that are present in food. So in any foods, you have lipids, you have proteins, you have carbohydrates. So in this particular schematic diagram, L stands for lipids, P stands for proteins. So what is the other constituent here?
Excuse me, ma'am.
Yeah.
Can you please repeat the question three? There was some network issue actually.
Uh,
The
okay.
last part.
Okay, so the last part in an enzymatic reaction, since enzymes are stable only at a certain small range of temperatures. So if you start reducing the temperature drastically, so the enzyme will be very sensitive to even small changes in the reaction conditions. So when you have a dissociation of the enzyme complex, so association and dissociation with the substrate is something that happens continuously. Your substrate will bind to the enzyme, it will dissociate from the enzyme. All these are very common processes. But if this happens at a very low temperature, your enzyme is very sensitive to very tiny changes in the conditions. So if the enzyme complex dissociates, this will rapidly result in a declination in the reaction rate. Uh, is this understood? If your enzyme complex dissociates at that low temperature, it will not be able to associate back. So you will have a declination in the reaction rate instead of an increase. Uh, we will be recording these sessions and we'll be putting it in YouTube as soon as possible. So in case if you guys miss the online classes also, you can refer to these offline, and if you have any doubts, you can post it there itself. In the discussion forum, and we'll get back to you.
Okay, ma'am. Thank you.
Okay, so continuing with question 4. So the other constituent that is majorly present in the food is the carbohydrate pool. Kindly mute your microphone if you're not using it for asking doubts or answering questions. Okay, so what happens when a lipid is oxidized? Any clue? What is produced if a lipid is oxidized?
Peroxides.
Yeah, so when a lipid is oxidized, it produces peroxides, and these peroxides bring free radicals will interact with other constituents present in the food, such as proteins, and that will result in changes in the pigments, vitamins, and flavors, and results in an off color, that is, undesirable changes. So what happens when so we discovered that one is the carbohydrate pool. So what happens when you subject carbohydrate to strong acids or base? So all carbohydrates contains a carbonyl group. They either contain C double bond O in the form of an aldehyde or a carboxyl group. So fructose and all will have an aldehyde group. Uh, sorry, a ketone group, and then your other sugars such as glucose and all will have a carboxyl group. So in those cases, you will always have a carbonyl group in carbohydrates. So when you subject the carbohydrates to hydrolysis, it produces reactive carbonyls. So all these reactive products such as peroxides, reactive carbonyls and all will start interacting with the other constituents that are present in the food, and when these free radicals react with other constituents, they produce some other pigments that are not natural to the color, natural to the food. So they'll start producing some other pigments, flavors, and all that might be off putting or something that is not preferable in most of the cases. So, so the answer to this question is option C, that is, your carbohydrate pool will react with acids and bases to produce reactive carbonyls, whereas your lipids will undergo oxidation to produce peroxides. Moving on to question 5. Match the reactions in column 1 with the food quality alteration in column 2. So it often happens that either through the natural processes that happen in the food itself, or while we are doing some food processing techniques, there are some kind of quality alterations that happen in food. So these can differ according to the kind of reaction that we are looking at. So are you guys able to match which reaction corresponds to which of the quality alteration? So what happens when you cut a fruit or so? Or any of the other reactions? Are you able to match it with one of the food quality alterations here?
Release of enzymes.
Yeah, so when you cut the food, you will have release of enzymes that are happening. You have cell breakage, and then you'll have release of enzymes. What about the other rest? What happens when you hydrolyze polysaccharides? That is something we discussed in the previous slide. What will happen if your uh, polysaccharides are hydrolyzed, or your carbohydrates are hydrolyzed? What happens?
Protein sugars
Yeah,
reaction.
so it will form carbonyl groups, and these carbonyl groups will now interact with other constituents such as proteins, and that will cause a protein sugar reaction. So one corresponds to D and 2 corresponds to C. And what about lipid oxidation? That is also something that we discussed in the previous slide.
That of flavors.
Off flavor, ma'am.
Yeah, so that will lipid oxidation will cause peroxides that will cause changes in the flavor and result in unfavorable flavors as well as textures. So heating of muscle tissue, any heating per se will inactivate enzymes because enzymes are all proteins and they work only in very small temperature ranges. If you move the temperature above or below its optimal temperature, its activity will drastically reduce. So heating of the muscle tissues or any heating per se will result in inactivation of enzymes. So the answer is option C. Hope this is clear. We'll move on to the next question. Okay. Which of the following statement is true in relation to the effects of solute on structure of the water? Solutes capable of forming hydrogen bonds, such as urea, may be expected to disrupt the normal structure of water. B. Inert solutes, such as hydrocarbons and non-polar groups of the compounds, like fatty acids and amino acids, do not have a structure forming action when introduced in water. C. In proteins, all the total amino acids have non-polar side chains. D. The total number of hydrogen bonds per mole of the solution will not substantially be altered as the disrupted water-water hydrogen bonds are replaced by water-solute hydrogen bonds. So which of these statements do you think is true?
C. C is true.
C or D? So, okay, so what happens when you add a solute forming, a solute capable of forming hydrogen bonds? Or let's not go to even that high. What happens when you add a polar group to a polar solvent like water? Why does it allow polar groups to be dissolved but non-polar groups to not be dissolved? So when you mix polar solutes such as urea and stuff, solutes in water, you will have your water-water hydrogen bonds. That is, your water and water will have hydrogen bonds that are formed, and these hydrogen bonds will be broken, and instead water solute hydrogen bonds will be formed, which is why polar compounds preferentially dissolve in polar solvents, because they are able to form the water solute hydrogen bonds. Whereas your non-polar solvents, no, your non-polar solutes cannot form these water solute hydrogen bonds. They will prefer to interact with themselves, whereas your water-water hydrogen bonds will remain intact. So when you add solutes capable of forming hydrogen bonds such as urea, you will not disrupt the normal structure of water, because your water-water hydrogen bonds will be replaced by water solute hydrogen bonds. Whereas in case of your non-polar groups such as fatty acids, it will not prefer to interact with waters, and hence the water-water hydrogen bonds will not be disrupted. Is this clear? So water-water bonds are disrupted in case of polar solutes, whereas to compensate for that, you have water solute bonds that are formed. Hence, the total number of hydrogen bonds per mole of the solution will remain more or less the same, because something is being compensated by some other kind of interactions. So this is true. Whereas in case of A, since it is able to form hydrogen bonds, it is not disrupting the structure of water. It is just enhancing the structure of water, or at least it is maintaining the structure of the water as it is. It will not disrupt the structure of the water. So statement A is false. Statement B is also false, because it will allow the water to interact with itself. Is this part clear, or is this confusing? And C is also wrong, because only 40% of the amino acids have non-polar side chains. There are some polar amino acids that have charged groups, charged side chains as well. So not all amino acids are non-polar.
Okay.
Is this clear, or do you want me to repeat this part again? Okay, so the answer to this question is option D. D is the only statement that is true. Rest of the statements are false. Moving to question 7. Solidification of an entire sample as a glass, that is no crystallization of the solvent or solute, is called which of the following processes? Amorphous, glass state, rubbery state, or vitrification?
Yes.
Why do you think that is the case? We're looking at the process, not the state. Solidification, or the process of the solidification of an entire sample as a glass, where there is no crystallization of solvents or solutes. So what is the difference between glass state, amorphous state, rubbery state? Any idea? I don't think this is there in lectures, but this is actually a part of your syllabus, because this was asked in your previous assignment and exam questions. So amorphous state is also known as a glass state. So basically amorphous state and glass state are the same. They refer to a non-crystalline state of the substance. That is, when you're cooling something rapidly, you're not allowing the food to form proper crystal structures. It's just basic random motion of the food particles are directly freezed. So there is no proper crystal structure as such. It is a non-crystalline state, but it is known as a glass state because of a certain it has a very glassy appearance, because your water now starts crystallizing. I mean, the water turns into ice, rather. I wouldn't use the word crystallizing. Your water turns into ice, whereas your solutes will still remain soluble in the very little liquid that is present. So if you start lowering the temperature, your water will start turning into ice, and any solute that is present in the food will remain in the very little water that is present. So now you will have a very super saturated solution. That is, your solute will be extremely concentrated. So at this stage, you will have very high viscosity of the sample, and this is known as the glassy state. Where you have very high viscosity, you have a supersaturated solution, and it is a non-crystalline amorphous state. So in this condition, only your water molecules, only small molecules like water will be able to have a vibration motion. Rest all will be completely frozen and will have a very glassy appearance. So that is why it is known as an amorphous state or a glassy state. Whereas rubbery state is the state of the food which has a viscoelastic nature. That is, it is both viscous, it is both elastic. So it has both the properties. It's same like a rubber. So rubber will have a certain amount of viscosity as well as elastic nature. So this foods will certain foods will have viscoelastic nature between its melting temperature and glass transition temperature. So below Tg you will have glass state. Between Tm and Tg you will have rubbery state. Is this clear? Let's say your food has a melting temperature of somewhere around 3 degrees or so, and your glass transition temperature is somewhere around -5 degrees. So your temperature between 3 and -5 degrees will have a rubbery state of the fluid, of the food. And this entire process of solidification into an amorphous or a glassy state without allowing crystals to form. And when I mean crystals, I mean proper ordered structures. Without crystallization to form, this process is known as vitrification. Is this clear? So the answer is option D. We're not looking at the state here, we're looking at the process here. So vitrification is the process of making an entire sample into a glass-like state without allowing the crystals to form.
एग कौन खाएगा? एग कोई खाएगा?
Kindly mute your microphone, please. So moving to question 8. Following: peak viscosity, paste stability, setback viscosity, and stability of the cooked paste. Are these terms that you're familiar with? Have you gone through the lecture?
नहीं हो रहा है क्या बना रही हो पॉपकॉर्न बना रही हूँ
So are you aware of these terms? Peak viscosity, paste stability, setback viscosity and all? Do you know where this comes in? Which concept?
Third unit, hydrogen water.
Okay, so are you aware of a certain process known as gelatinization of starch?
Yes, yes, correct.
So when you take starch granules and you add water to it and start heating it, it starts forming a paste. When you start mixing it, it starts forming a paste. So this is known as gelatinization of starch. So over the process of gelatinization, you can see drastic changes in the viscosity of the paste. So it is given by this particular graph here. So as time increases and you increase the temperature, so you first add water to your starch granules. When you add water to the starch granules, your starch granules will start taking in the water and will start swelling. So when it starts swelling, you can actually see a rise in the viscosity. Why does that happen? The initial rise in viscosity, why does that happen?
Because of temperature.
So temperature should ideally decrease the viscosity. Why is it increasing the viscosity here? Temperature will have an effect on viscosity, no doubt. But in this case, why are we seeing an increase in viscosity?
Starch molecules absorb water and starts to swell.
Yeah, if you swell, then you'll have bigger particles, and the bigger particles start colliding with each other. They will not be able to flow as rapidly as they used to flow once when they were not swelled. So smaller particles.
డార్లింగ్ వాక్ చేయగలవా నువ్వు?
Sorry?
నడుస్తావా?
So
బేసిక్ గా నాకు అక్కడికి కాస్త పిచ్ అన్నమాట. రోడ్డు మీద నడుచుకుంటూ పోతాం.
So when your starch granules start swelling,
వచ్చేప్పుడు ఆటోకి వచ్చేద్దాం.
you'll have larger
ఎక్కువ ఉంటాయి
particles.
కాబట్టి 90% డేటానా డేటా ప్యాకింగ్ లేదో మొన్న గారు రీఛార్జ్ చేసింది.
So when you have starch granules that are very large in size, they will impede the flow. That is, the moment you'll have resistance to flow. The moment you have resistance to flow, you'll have a higher viscosity that is coming in. So when you keep, when the starch molecule starts swelling up over and over, at one point of time you'll have something called as a peak viscosity, above which the starch molecules will no longer swell up and the viscosity will no longer increase. Is this clear? So peak viscosity is the highest apparent viscosity obtained during pasting process.
Yes, correct.
So what happens after that? What is paste stability?
Resistance to breakdown.
Yeah, so paste stability is the resistance to breakdown. So how do you calculate that? Peak viscosity, we can keep on increasing the temperature till 95 degrees or so, and you'll keep measuring the viscosity. The maximum viscosity that you will get is the peak viscosity. How do you measure the paste stability or the resistance to breakdown? So you can see here in the graph, this curve corresponds to the temperature. So at a certain region, you are seeing that the temperature is constant, somewhere around 95 degrees. So what we'll do is, once your starch has swelled up, it will and you start getting a paste-like thing. To now figure out if the paste is stable or not, we'll keep stirring the paste at 95 degrees continuously, and you'll see you will keep measuring the apparent viscosity at that stage. So you can see here, when there's a holding time, your viscosity starts decreasing. So why is there a decrease in viscosity now? Why is it not stable?
Breakdown.
If it was only depending upon your temperature or so, ideally when you stabilize the temperature, your viscosity should also have been stabilized. But here you can see that there's a drop in the viscosity after it reaches the peak. And this drop is because now you have, when you're continuously mixing, your swelled up starch particles will now undergo shear stress and will start breaking. The moment you start breaking the starch particles, now you'll have smaller fragments. So now it is no longer difficult to stir the process, or now the viscosity is no longer that high once you break the starch granules. So this breakage of the starch granules results in a decrease in the viscosity, and this is what is known as the breakdown. So this will tell you how drastically this drops, will tell you how stable is the paste. If there's a very less drop, which means your paste is stable. If there's a drastic drop, which means your paste is not stable. So this is measured at very high temperature, somewhere around 95 degrees, for 20 to 60 minutes by stirring it continuously. So what is setback viscosity?
Cooling of viscosity.
Yeah, so you're cooling the paste to 50 degrees now. So after it was there for 95 degrees for so long, now you're cooling it to somewhere around 50 degrees. So at that stage, you can again see there's a rise in viscosity. This rise in viscosity is because once you started cooling down, all your molecules will start coming together. And once your molecule starts coming together, these will form hydrogen bonds in between. So intermolecular hydrogen bonds will start forming. So now, since bonds are starting to form, you'll again have a more thicker substance that is forming, and hence a higher viscosity. This is understood. As you cool down, your bonds start forming, and hence you'll see a high viscosity that is increasing continuously. So this is known as the setback viscosity. That is the viscosity after you cool it down to 50 degrees. And the stability of the cooked paste is your viscosity after stirring at 50 degrees for up to 1 hour. So you leave it at 50 degrees, you'll keep stirring it for 1 hour, and then you'll measure the apparent viscosity. That will be your final stability of the cooked paste. So when we are gelatinizing starch during the food processes, these are the 4 things that you'll need to calculate. That you'll need to calculate the peak viscosity, how stable is your paste before cooking, and what is the setback viscosity, that is after you're cooling down, what is the viscosity, and how stable is that paste. So peak viscosity corresponds to highest apparent viscosity. Paste stability is what happens as the resistance to breakdown, that is at 95 degrees, how long it is able to maintain that apparent viscosity or how drastically it is changing. Setback viscosity is what happens after cooling it, And stability is what happens when you cool it down and stir it for 1 more hour. So the answer is option C. So this is also very well explained in the lecture 5. So if you guys have any doubts, you can refer to lecture 5 as well, or you can post your questions in the group chat. Okay, moving on to question 9. Which among the following polysaccharide molecules have an egg box junction cross-links? So all these options that are given, gelatinins, carrageenans, amylase and alginates, are all polysaccharides that have a habit of forming gel-like structures. So these gel-like structures have different kind of junctions that enable this gel-like structure to form. So any clue what an egg box junction is?
B. Alginate.
So this is how an egg box junction will look like. So this is formed only in the case of alginates. At least in these four, among these four options, it is formed in the case of alginates. So what happens is that alginates are negatively charged polysaccharides. So these alginates will arrange parallel to each other, and within the distance, that is within the between the two parallel polysaccharides, alginate polysaccharides, it has enough space to accommodate divalent cations like calcium, magnesium and all. So these negatively charged alginates will attract the positively charged calciums, which will now form a bridge between these two chains. So you'll have a negative charged alginate, you'll have a positive calcium, and then you'll have a negative charged alginate again. So these will form a bridge-like structure. So this bridge-like structure or a crosslink is known as the egg box junction. So since these are charged bridges or so, that is these bridges involve charged interactions, they are very, very stable and are melted or broken only at very high temperatures. So these gels that are formed are very strong, and generally charged residues are what is involved in an egg box junction. Is this clear? So you have other types of gels as well. You have polysaccharides that can form helices. You have polysaccharides that can form microcrystallites and all. So different kind of polysaccharides can form different kind of structures based on the kind of interactions that they can undergo. The moment you have charged interactions, an egg box junction is formed, and this is possible only because alginate is negatively charged and it can interact with calcium ions. Hope this is clear.
Yes, ma'am.
So amylases can form microcrystallites, carrageenans can form helical structures. So all these are present in the food chemistry book that I referred to in the previous slides. You can go back and you'll have a much deeper insight into what are the different kind of gel formations that can happen in different kinds of foods. So the answer is option D.
Yeah.
Moving to question 10. Which of the following statement is correct with respect to starch retrogradation? The extent of retrogradation does not depend on the water content of the starch. The amylose lipid complex does not interfere with the recrystallization of amylopectin, which retards retrogradation. The structural difference found in amylopectin chain causes different rates of crystallization, and higher temperatures above 15 to 20 degrees Celsius reduces retrogradation. So before we go into the question, does anybody know what retrogradation is? So any clue what retrogradation is when it comes to starch?
Reduction the temperature.
So once your starch forms a gel or so, sometimes it has the ability to reassociate and recrystallize. So your starch will come together, it will aggregate, it will recrystallize, and this process is known as retrogradation. So your extent of retrogradation, that is the extent to which your starch can recrystallize, depends upon various kinds of factors. So your extent of retrogradation does not depend on water content of the starch gels. Is it true or false? What do you think is the answer?
False.
The answer is false, because when there is extremely high water content, what will happen is that everything will become very dilute. So now your starch will not be able to come together and aggregate. So there's a certain concentration that is required, certain water content that is required to enable retrogradation. If it becomes very, very dilute, it will not be able to retrograde or come together. So A is false. It does depend upon the water content of the starch gels. So what about B? The amylose lipid complex does not interfere with the recrystallization of amylopectin, which retards retrogradation.
False.
Okay, so what is starch made up of? Before we go into why this is false.
Carbohydrate. It's a carbohydrate, not a lipid.
Sorry?
Carbohydrate.
No, the actual components. What are the two components that starch is made up of?
Amylose, amylopectin.
Yeah, and what is the difference between
Amylase and
amylose and amylopectin? Major difference?
Amylose is a straight chain of molecules and amylopectin is branched.
Exactly. So, since amylose is straight, its ability to recrystallize is better. And since amylopectin is branched, it will kind of hinder the other amylopectin molecules to come together. Because it is branched, it will have some steric hindrance, or basically, it will not allow it to come very close together. So, the ability of amylopectin to recrystallize is very less, whereas the ability of amylose to recrystallize is more. So, what will happen if your lipid starts interacting with amylopectin? So, retrogradation is basically so what happens is, after you have formed a paste or so, that is after you have formed a starch paste, if you leave it like that, sometimes your starch will have the ability to come, starch molecules will have the ability to come close together. It will aggregate, and this process is known as retrogradation. This happens in a gelatinized starch. So, what will happen if your lipid molecules now start interacting with amylopectin? Amylopectin is itself not able to retrograde as good as amylose. So, the moment you have now a lipid complex also coming in, this will further prevent retrogradation. Okay, so the lipid complex, the amylose lipid complex, will definitely interfere with the recrystallization of amylopectin, and it will retard the retrogradation. So, B statement is also false.
False.
So, what about C? The structural difference in amylopectin causes different rates of crystallization.
Correct.
Yeah. So, depending upon what source you're looking at. So, when you're dealing with food process technologies, you'll have different sources from which you will take starch. It need not be one specific source, or it might not be a homogeneous source. You will have a heterogeneous source from where you'll be taking starch. And each of those components will have a slightly different structure of amylopectin. That is, the amount of branching might be different. Your extent to which it is branched and where all those will be different. So when you have so much differences in the amylopectin chains, that will also cause a difference in the rate of crystallization. Had it been very homogeneous, it will not affect the rate of crystallization. But since amylopectin is a branched chain, the extent of branching and all will drastically affect the rate of crystallization. So option C is true. And option D, higher temperatures above 15 to 20 degrees Celsius reduces retrogradation, which is false. Only above the room temperature, that is 32 to 40 degrees Celsius, is what will decrease the retrogradation. That is, it will not allow the molecules to come together and crystallize. Only at higher temperatures. At 15 to 20 degrees Celsius, it is a pretty normal temperature for the starch to come together and retrograde. So the correct answer to this question is option C. Option C is the only statement that is true. The rest are all false. And for retrogradation to happen, you generally require a water content of somewhere around 40 to 45%. If your starch has more amount of water, then it becomes very, very dilute and it will not retrograde. Okay, moving to question 11. The storage of starch gels with water content dash and at low temperatures, but having the glass transition temperature of approximately dash increases retrogradation. So the first part of this question is something that we discussed in the previous slide itself. So what is the answer to that?
A.
Okay, 45 to 50% is what the water content should be. But should the glass transition temperature be 5 or minus 5 degrees Celsius?
Okay, that's no correct. Comma is there. B, A or B?
Yeah. So what happens when you maintain the starch at a temperature higher than your glass transition temperature? What happens when you maintain it lower than the glass transition temperature? So if you remember in my previous slides, what happens when your food is below TG? TG is the glass transition temperature. That is the temperature below which your food will become like a glass-like substance or an amorphous substance.
Correct.
So
Then-
if you maintain your food below your TG, everything will just freeze. If you freeze everything, freezing is completely different from retrogradation. Retrogradation involves crystallization, coming together and aggregation. So if you just freeze the sample, it is not equivalent to retrogradation. So you need to maintain the temperature above the glass transition temperature so that you still have some amount of mobility present, and that will allow the molecules to come close together, form hydrogen bonds and then recrystallize. So your temperature should be above your TG.
Correct. Minus.
Just a minute. So in this case, since your retrogradation has to happen at low temperatures, you need to make sure that the TG is even lower. So in that case, your TG should be somewhere around minus 5 degrees Celsius, and your process should happen at a very cold temperature with 45 to 50% water content for the molecules to come close together, aggregate and form a kind of a gel-like substance. So the answer is option B. Are you able to understand why it is not A and why it is B?
Yes, ma'am, understood.
Okay. Moving to question 12. So here, match the following. We are having different kinds of bound water and what it does in the other column. So are you aware of the concept of bound water? What does bound water mean? Okay, so when any kind of food material, or even if you add some solute to a water a solvent such as water, you will have something known as the bound water. Bound water can be visualized like one single layer of water around your solute molecule. So if you have something like protein that is added in water, there will be a water surface or a small layer of water that surrounds the protein. So this particular layer is known as the bound water. And there are different types of bound water depending upon how much it is bound, the extent to which it is bound. So you have type 1, type 2, type 3 and type 4. So each of these have difference in the amount of water that is bound and hence the amount of activity as well. Is this clear? I'll explain the differences in each of these classifications. So you have 4 classifications based on how much the water is bound. So bound water decreases and the water activity is increased in the order type 1, type 2, type 3 and type 4. That is, type 1 is the most bound water. It is very, very difficult to remove this water from your tissues or from any food particles that you are looking at. Type 1 bound water is extremely difficult to remove and it can be only partially removed with the help of dehydration. So type 1 bound water has the maximum amount of bound water that is present and hence it has very low water activity. Water activity is only present if your water is free and is able to move all over and all. If it is bound, it will have very less water activity. So type 1 bound water, since everything is bound, you will have very less water activity and it is very difficult to remove this from your food molecules as well. So 1 corresponds to B. Now as you increase the classification, your amount of bound water reduces. That is, type 2 will have slightly lesser amount of bound water. So since now a little more water molecules are available in the free state, it is now available for enzymatic activities that are only hydrolytic and non-enzymatic browning. Is this clear or is it confusing? So type 1 is most bound, type 4 is not at all bound. Something like that. There is a gradual increase. Type 1 is most bound, type 2 is slightly less bound, type 3 is slightly even lesser bound, and type 4 is completely free. So since depending upon the availability of water molecules, there are certain reactions that can happen, because all reactions require water, and it requires certain amount of free water for the reaction to happen. So type 2, since majority of the water is bound and only very less are available, only hydrolytic enzymatic activities and non-enzymatic browning activities can take place. And if you remove type 2 water also, so all these enzymatic activities will also be removed, and it will be very difficult. It will be very good for the food to be stored in that particular condition. If none of the activities are working, none of the enzymatic activities working, none of the non-enzymatic browning activities are working, your food will remain stable for a much longer time. And your microorganisms will also not grow if you remove the type 2 bound water. Is this clear?
Yes.
And type 3 has a little more free water present. So since more water is available, this will be available for both hydrolytic and oxidative enzymatic activity and non-enzymatic browning. So if you take a human tissue or a meat tissue or anything, type 3 bound water is what is majorly present. After you remove type 3 bound water, you will have to remove type 2 bound water also. Then only you will be able to store these food products. Because that is when you will have very less amount of water present, you will prevent all enzymatic activities and microbial growth. So type 3 is what is present generally in tissues, and it is available for hydrolytic activity, oxidative activity, as well as non-enzymatic browning. Sorry, any question? And type 4 bound water is the one that exists it is not at all bound, it exists in a free state. So 1 corresponds to B, 2 corresponds to C, 3 corresponds to D, and 4 corresponds to A. So the answer to this question is option D. So there are different kinds of bound water. This is also explained well in, I think, lecture 4. If you have any doubt, you can post it in the group chat. I'll explain it again. Moving on to question 13. Which among the following statement is not correctly defining the bound water? Bound water is the equilibrium water content of a sample at some appropriate temperature and low relative humidity. Bound water is that which does not freeze at some arbitrary low temperature or lower. Bound water is that which contributes significantly to the permittivity at high frequencies and therefore has its rotational mobility restricted by the substance with which it is associated. And bound water is that which exists in the vicinity of the solutes and non-aqueous substances and has properties differing significantly from that of the bulk water. So I know this is a lot of concepts here, but are you able to, with the previous explanation, are you able to guess what the answer could be here? I'll explain each and every statement one by one. But what is the answer that you think here?
A.
No, A is actually correct. So what happens is bound water is the equilibrium water content. So at any temperature or any relative humidity, there will
Not
be
correct.
some amount of bound water that is present in your tissues, in your food samples and everything. So A statement is actually correct. That is how you define bound water. It is the equilibrium water content of a sample at a certain temperature and relative humidity.
Low relativity, correct. Okay, question is not incorrect.
And B is also correct because since bound water is present inside your tissues, inside your food products and everything, it is not that does not freeze that easily at low temperatures, like say minus 40 degrees Celsius or so. Bound water will always remain liquid at such low temperatures because it is always present in the form of next to solutes. So what happens to the freezing temperature when you have solutes? This is a concept that we've learned in probably high school or so. What happens to water's freezing temperature when you have solutes?
In bulk, it will bulge.
It decreases.
So there's something called as freezing point depression. The moment you add solutes like say sugar, salt and everything into water, the freezing point will no longer be at 0 degrees. It will be even lesser. So bound water is always next to some kind of solute. It is always present with next to some kind of a solute, and hence that bound water's freezing temperature will not be the same as that of the bulk water. If bulk water's freezing temperature is 0 degrees, bound water which is present next to the solutes and other substances will always have a freezing temperature much lesser. So your bound water will not freeze that easily. Is this clear? The freezing point depression? And see, since bound water is continuously in the presence of solutes, it will always experience some kind of forces. All the solutes will exert some kind of forces on this bound water, and it will not allow it to react in the same way that the bulk water would react in terms of permittivity. That is, waters will have a higher permittivity. The bulk water, since it is free moving, it will have a higher permittivity, whereas bound water, which now experiences a lot of forces with respect to the solutes and all, will not be able to have that much amount of permittivity as the bulk water. Is this clear? So the bound water has very low permittivity, whereas the bulk water has higher permittivity. Since the bound water is extremely restricted in terms of its ability to move and everything, all the properties will be very different from that of the bulk water. The freezing point will be different, the boiling point will be different, everything would be different. So since free water has a higher permittivity, bound water which is continuously restricted will have a lower permittivity. So C is the statement that is false. So there are multiple other statements that define bound water. There is not one single definition for bound water, because it's a very confusing concept. So there are multiple statements for the definition of bound water, and all these are present in the food chemistry textbook as well, and it's readily available in the internet as well. So all the definitions of bound water are present, and the answer to this question is option C. Option C is the one that is false. It has low permittivity. Moving to question 14. Dash are a group of homologous oligosaccharides obtained from the breakdown of starch by the action of cyclodextrin gluconeotransferase produced by Bacillus macerans. What do you think is the answer? Do you guys know what is cyclodextrin? So cyclodextrins are oligosaccharides that are arranged in a cyclic manner. So you will have somewhere around either 6 or 7 or 8 glucosyl units. So all these glucosyl units will be arranged in a ring-like manner. That is, it will form a donut-like shape or a ring shape, and these are known as cyclodextrins. So cyclodextrin gluconeotransferase is one of the very important enzymes that are produced by Bacillus species. So these enzymes form rings of 1 to 4 alpha-linked glucopyranosyl units. So you'll have glucosyl units arranged in a ring-like fashion by the help of 1 to 4 alpha linkages. And these molecules are known as cyclodextrins. Cyclodextrins are also known as Schrödinger dextrins or cycloamyloses. So all these three are pretty much the same molecules. They're just different names of the same molecules. And this enzyme breaks down starch into cyclodextrins. And this seems to be a very important enzyme in the food product industry.
All the
So answer is all of the above. All these three are pretty much the same molecules, and the starch is broken down into 6, 7 and 8 membered rings, also known as the alpha, beta and gamma cyclodextrins. So answer is option D. Moving to question 15. Which of the following reactions commonly does not depend upon sunlight? So any clue? Conversion from ergosterol to cholecalciferol, rancidity of sesame oils, protein denaturation, and chlorophyll degradation. Which of the following, all of these affect your
Option A.
sorry?
protein denaturation.
Yeah, correct. So protein denaturation is completely reliant upon the temperature and presence of any denaturant like say urea or guanidine or so. So only in the presence of some denaturing chemicals or in the presence of temperature will your protein denature. Otherwise, your protein denaturation does not depend upon sunlight. So, but all of the other three reactions depend upon sunlight. So, conversion of ergosterol to cholecalciferol. Do you know what is cholecalciferol?
Vitamin D.
Yeah, vitamin D3 is cholecalciferol, and that is produced in the presence of sunlight, specifically UVB. So, UVB is required for the production of cholecalciferol, and hence this reaction depends upon sunlight. And the rancidity of sesame oils. So if you leave sesame oils in the presence of air and heat, like say in the presence of heat that is produced upon sunlight, or if you leave it open in the air also, oils will undergo rancidity. And again, you have chlorophyll degradation also. You can see the yellowing of leaves and all in autumn seasons as well. So that will happen when prolonged exposure to UVB will result in chlorophyll degradation, and that will result in loss of color in foods. So all the rest of the three reactions are dependent upon sunlight, whereas protein denaturation is dependent only upon the presence of chemicals or temperature. So the answer is option C. Moving to question 16, match the following: hemagglutinin, thiaminase, avidin, and phytates. So do you see any common feature among these four compounds? What is the common property of all these four compounds: hemagglutinin, thiaminase, avidin, and phytates?
These are anti-nutrients, ma'am.
Yeah, so these are anti-nutrients and are not preferred to be consumed or
Consumed,
they are
okay.
deemed not fit for consumption. So can you match which anti-nutrition is corresponding to which of the food product?
D.
So what does hemagglutinin correspond to?
Egg.
Yeah, so hemagglutinins are
D.
protein molecules that result in agglutination of your erythrocytes or your RBCs. And they often result in inhibition of growth as well. Under certain severe cases, they will inhibit the growth as well. So hemagglutinins present in legumes are deemed unfit. What about thiaminase?
Fish.
Yeah, so your raw fish, your shellfish and all have thiaminase, and these break down thiamine or vitamin B1. So when you have a breakdown of vitamin B1, you will no longer have the same kind of nutrients that will be present originally, which is why people are often skeptical about consuming raw fish such as sushi. So sushi and all will have raw fish that will have thiaminase in it, and since it is an anti-nutrition compound, it is not preferred to have raw fish in bulk quantities. So thiaminase is present in fish that will break down B1, and avidin is present in eggs. So avidin, what it does is it will bind to biotin and it will make it unavailable for absorption. So avidin as such is directly not involved in some kind of anti-nutrition, but it will bind to biotin and make it unavailable. Same goes for phytates as well. Phytates are present in cereal grains that will bind to ions such as calcium, magnesium, zinc and all, and that will make them unavailable or for absorption. So hence, it needs to be made sure that the food that you are processing should be free of these anti-nutrition compounds, and hence certain processes are done, like say some kind of heat inactivation or is done to inactivate these kind of enzymes or proteins to make sure that it is deemed fit for consumption. So the answer is option D. So moving to question 17, an HLB less than dash favors water in oil emulsions. A value greater than dash favors oil in water emulsions. So what is an HLB? Any clue what is an HLB? So HLB stands for hydrophile lipophile balance. So there are certain compounds known as surfactants that will have a kind of a bridging activity between your lipids and your water. So and the ability of the surfactants to perform its function depends upon a parameter known as HLB or hydrophile lipophile balance. So depending on the value of this HLB, you can figure out what kind of emulsions it can form. So what happens when you have a very high HLB? It's hydrophile to lipophile. Hydrophile is in the numerator, lipophile is in the denominator. So what does it mean when you have a very high HLB? So when you have very high HLB, it means it has more hydrophilic behavior than lipophilic behavior. The moment it has hydrophilic behavior, it will prefer to remain in water. Whereas when it has very low HLB, it means lipophilic characteristic dominates. So it will prefer to remain in oil. So surfactants have this important property called the hydrophile lipophile balance, and a surfactant, and it generally ranges from 1 to 20. So emulsions will have a range from 1 to 20 HLBs, and if you have a surfactant having a HLB of 7, it means it will be preferred in both water as well as oil. If you have an HLB less than 6, which means your lipophile dominates, your ability to remain in oil dominates, and hence that will favor water in oil emulsions. So any examples of water in oil emulsion?
Butter.
Yeah, so butter is a very common water in oil emulsion. So if you're dealing with a surfactant less than HLB, it will HLB less than 6, it will prefer to remain in water in oil emulsions. Whereas that greater than 8, so now your hydrophile starts to dominate, which means it will prefer to be in water. So now it will be in oil and water emulsions. So based on the HLB value, you can actually figure out what kind of emulsions they will be forming. And based on that, you can add those additives to make such emulsions in the food processing technologies. And those emulsions with 7 to 9 are known as good wetting agents. The answer is option C. Below 6 is water in oil, above 8 is oil in water. So question 18. Which of the following is an undesirable change during food processing and storage? A. Chemical alteration of polymers by hydrogen bonding, hydrophobic clustering, and cross-linking. B. Gelatinization and chemical modification of starch, glucose isomerization to fructose. Control of enzymes mainly by heat denaturation, and cooked notes in ultra-high temperature milk. So which among these four do you think is an undesirable change during your food processing?
First one.
Not necessarily. Sometimes we deliberately make sure that the polymers undergo alteration to change our texture. Like say, as I was talking about starch gelatinization and all, sometimes we deliberately do a kind of starch gelatinization and all to chemically alter the polymers, alter its hydrogen bonding, and hence this is not necessarily an undesirable change. Sometimes we do it deliberately as well. And glucose isomerization to fructose and all is very much desirable because fructose is a more sweet, it has a more sweet taste. So if you isomerize glucose to fructose, you will be able to increase the amount of sweetness in a certain food product. So option B is also favorable. And option
Then
C,
D.
yeah, option D is unfavorable. Option C is favorable because you don't want enzymes to spoil your food. If you have enzymes, it will undergo lipid hydrolysis, it will undergo oxidation and stuff. You don't want the food to turn bad, so you control the enzymes by denaturing them. So if you inactivate the enzymes, your food will remain more stable. So it is a desirable change. Whereas D, when you have ultra high temperature milk, that is, you rapidly change the temperature of the milk to sterilize it, often what happens is it will have a very cooked taste. As if you keep the milk for a long time in a heated condition, it will often have a different taste when compared to that of a fresh milk. So these kind of cooked notes are not very much preferable in milk-based food products. So option D is not favorable. This results in changes in the flavor, and in the long run, this will not be favorable for milk. The answer is option D. Okay, question 19. Which of the following is not related to instability of foam? So what is a foam? What kind of an emulsion it is? Is it an oil in water or water in oil?
Water in oil.
Are you sure? Have you ever seen butter foaming? It's an oil in water emulsion. So
Oil in water.
the stability of the foam depends on multiple factors. So you have four options here. What do you think is related to is not related to the instability of the foam?
Aeration.
Yeah. So if you have a substance or an emulsion that has the ability to foam, if you aerate the sample, you will actually have more foam that is forming instead of less foam. So option D is correct. But what about the rest three? Do you know what the rest three options are? What is Ostwald ripening? So in a foam, you have small bubbles, you have big bubbles. So what happens in an Ostwald ripening is that your small bubbles will become more and more smaller, and your big bubbles will become more and more larger. This is because whatever air was present in the small bubbles will start moving to the bigger bubbles. The air will start moving. The bubbles will not coalesce. Coalescence is a different concept. Your air will move from your smaller bubble into the liquid into the bigger bubble. So now your smaller bubbles will become smaller, your larger bubbles will become larger. And we know that large bubbles are not very stable. They will pop very easily. So Ostwald ripening will transfer the air from smaller to larger bubbles, making it even bigger, and that will result in popping of the bubbles and instability of the foam. So that is what Ostwald ripening is. Drainage is basically if you remove the liquid. If in a foam, if you remove the liquid, that that will cause actually instability of the foam. Your bubbles will start popping, or whatever bubbles will start. I mean, it will actually start popping, and hence drainage of the liquid will actually cause instability of the foam. If you drain one of the major dispersing medium itself, then it will start to become unstable. So drainage of the liquid will also cause instability of the foam. And coalescence, as we say, smaller bubbles will come together to form a bigger bubble, and that will also pop. So there are three options: Ostwald ripening, drainage, and coalescence leads to a popping of the bubbles or instability of the foam. Whereas aeration, when you supply air, that will increase the foam stability. Hence, answer to this question is option D. So the last question for the session, question 20. Match the following: hazards inherent to foods, hazards associated with environmental contaminants, arising from microbial activity, and food processing. So which corresponds to what? So hazards inherent to foods will come under allergens. So certain people are allergic of gluten, lactose, and everything. So those are all not something that we introduce into the food. Those are normally present in the food, inherent to the food itself. So the hazards inherent to foods include your allergens that people are allergic to. So one corresponds to D. So what about environmental contaminants?
Radionuclides.
Yeah. So you have all these pollutants and everything that will introduce radionuclides into your food. So hazards associated with environmental contaminants are radionuclides that come from pollution and other kind of toxic substances that are present in the environment. So hazards from microbial activity corresponds to mycotoxins. So as it is very obvious from the word itself, mycotoxins come from microbes such as fungus. So if you have fungus that excretes some kind of a toxin or so, that will remain as a hazard for your food. So hazard for microbiological activity corresponds to mycotoxins. And hazards emerging from food processing will be the last option, that is chloropropanols. So what happens to chloropropanols is that often in kind of food processing technologies, you hydrolyze a lot of foods, like say some kind of vegetables and everything. You hydrolyze them, and this hydrolysis happens in the presence of strong acidic conditions. So often you see that food processing technologies will often use hydrochloric acid or some kind of acidic conditions, and under these conditions, you'll have very toxic chemicals such as chloropropanols that form. So these are hazards that arise from the food processing techniques that we use. So we need to ensure that all our food processing techniques have chemicals or so that are either fit for consuming themselves or do not produce such kinds of side effects or byproducts. So the answer to this question is option B. So this was the last question for the session, and this was the entire syllabus that corresponded to week 1. Tomorrow also a repeat of this will be done. So in case you guys missed any questions or you have any doubts, you can ask the other TA. Some other TA will be coming to explain the same concepts again. So if you have any extra questions also, you can post it in the group today. We will clarify it tomorrow, or you can post it in the discussion forum that is present in the NPTEL, and we'll clarify it either there or in the other live sessions as well.
Okay.
So any doubts so far in this particular session that needs to be clarified? Any question that needs to be repeated?